Okay, this is Physics 1C for April 2nd, 2020. What we're talking about today is magnetic flux and so on and so forth. First, magnetic flux. That's the first thing we want to talk about. So in order to discuss this, I've got some pictures here. Let me move some of this stuff off to the side. All right, so magnetic flux. What is magnetic flux? So we learned about electric flux, and magnetic flux is very similar. So magnetic flux, we use the symbol phi with a little b to represent magnetism. And this is basically going to be equal to magnetic field multiplied by an area and then multiplied by a cosine of an angle between the two of them. So it would be like, suppose you've got a magnetic field in space. Let's say it points like in this direction here, like just to the right. That's your magnetic field. And within this magnetic field, you place some type of a surface, like maybe just some type of sheet, for example, that has an area A. And then to get the flux for this, you would just take the field times the area. But then if the area vector was tilted in some way, so if you had a sheet, let's say, that was coming kind of out towards you, so there's our sheet. If it's tilted in some way, what we do is we say you can draw an area vector, which points normal to the surface, that points kind of like this. And then if there's an angle theta between the two of them, we just say flux is given by that expression, or more generally as just the dot product between B and A. Magnetic flux is extremely important. We saw in the previous section, like chapter 2, whatever, we learned about Gauss's law and saw how Gauss's law could be used to describe how you find electric flux. And while electric flux was useful, it was useful for finding electric fields. That was about all we could do with it up till now. We're going to see that magnetic flux plays a huge role in terms of the interaction between electricity and magnetism. So magnetic flux is extremely important in terms of what it does. So that's our general definition, okay? More generally, if your surface is not flat like this, then we have to use the same kind of thing that we did with electric flux, where we define this to be some type of an integral of B dot dA, just as we did before. Now, I put two examples of magnetic field lines here because I wanted to talk to you guys about one of the properties of magnetic flux that's kind of interesting. So this is a set of two magnets that are pointing north end to north end, and the lines that are drawn here are your magnetic field lines, right? So one thing you can do is you can say, suppose that I take a surface like a circle, okay? And here, let me make it a different color. Oops. Do I do that by like selecting this and then doing shape and then doing this? Will that do it? Yeah, it will. Okay. So suppose that I take a little, I love that I have to keep reselecting this. Okay, suppose that I take a circle here like that. And I ask the question, in terms of that little circle right there, let's suppose that that circle is actually a sphere. What if I ask the question, what is the flux through the sphere? Does that question make sense to you guys? And I'm going to remind you another thing about flux, which is really important, which is that if you have flux that goes in, it's positive, and if it goes, no, the other way around. If it goes in, it's negative, right? So lines coming in. These give you negative flux. And then lines that are going out of your surface, going out, give you positive flux. It's also the case that the flux ends up being proportional to the number of lines that either go in or out of your surface. Oh god, that looks awful. It's proportional to the number of lines that penetrate the surface. Right? So what do you notice about this green sphere that I put in here? What do you guys think if we just count in terms of lines, okay, because the flux is proportional to the number of lines. If we just count the lines, how many lines do you see going into our surface? Someone answer that question. I see 5. Do you guys agree? 5? Yeah, someone else put 5 in the chat, right? There's one right here, one right here, 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 and here. That's 5, right? And how many lines go out of the surface? 5, right? So what's the net flux? 0, right? The net flux through the sphere is 0. Right? Okay, now what if I took this sphere, the same sphere? I think I can, like, nope, not gonna let me. I think I can just move it. What if I move it like here, right around the South Pole? What's the answer now? How many lines actually? Hold on a second. Let me make sure this is gonna work. It's not showing all the lines. There's lines inside of the magnet, by the way. I mean, I can draw them on here. It's not going to look great, though, because they're so bunched up. But there's actually lines that... This is not... I picked a really bad picture for this. These lines, for example, like right here, this one actually goes through the magnet like this. And the one on bottom also goes through the magnet like this. I don't even know if that's enough to show you. I didn't try this before class. I just found a picture and I was like, certainly this is going to work. My argument would be that no matter where I put this circle on the picture, you're always going to see the same thing. Like if I put the circle right here, how many lines are going in? There's 1, 2, 3, 4, 5, 6 that come in, and then there's 6 that come out, right? Can you guys all see that? And if I moved it, whoops, if I moved the circle like down here, it'd be like 1 line comes in, 1 line goes out, 1 line comes in, 1 line goes out. The thing about magnetic field lines is they always form closed loops. They always form closed loops. So what that means is that anywhere you put your surface, the net flux is going to be 0. So in general, if we want to find the flux through a closed surface, the answer is always going to be 0 when you're talking about magnetic fields. We can compare this to what we got for electric fields. For electric fields, we got what was called Gauss's law, right? If I take the integral of E dot dA over a closed surface, this ends up being equal to the charge inside divided by epsilon naught. So these are both different expressions of Gauss's law. It's just that this one is Gauss's law for magnetism. It says that the net flux through any closed surface, net magnetic flux, is always 0. Sorry, just the top one. They're both Gauss's law, but this one is Gauss's law for magnetism. It's the second of Maxwell's equations that we learned about in this class. Okay. Does that all make sense to you guys? Yeah. That's exactly right. All magnets are dipoles. There are no magnetic monopoles. That's what that says. That's what this equation says. It says that there's no magnetic monopoles. There's no such thing as charge for magnetism. If there was, we'd put magnetic charge over here on the right-hand side. But there's no magnetic charge. It doesn't exist. We've never found one. We keep trying, but we can't find these magnetic monopoles. All right, so there's the second. We've now got half the class done. Half of Maxwell's equations we now know. And there they are right there. The only thing we now need to talk about, these two describe, in effect, all of static magnetism and static electricity are described by these equations, things that don't move. But we've already started learning that charges can move, and they produce this thing called current. And what we're learning in this chapter is this idea of magnetism, and what we'll learn in the next chapter is that the connection between electricity and magnetism is that the moment you have charges that are flowing in a circuit, they produce magnetic fields. And that's really what the rest of the class is about, is the way in which current-carrying wires can produce magnetic fields and how we can use moving magnets to produce electric currents. And that's really what 1C is about learning how this phenomenon called electricity, when you make it so that the electric parts move and you create a current, you also produce this thing called magnetism, and magnetism and electricity kind of interact with each other in this kind of, one produces the other one and vice versa. They kind of can create each other. And that's what the rest of the class is about, is describing how that process works. All right, do you guys have any other questions about this? Okay, if not, we're going to move on to this, the circular motion of a particle in a magnetic field. I talked about this briefly at the end of class last time, so I'm going to go ahead and just review what we said and then add on some new things. So and we're only going to talk specifically here about a uniform field. Okay, so we start off by saying that we have some magnetic field lines, and let's say that there's a uniform magnetic field that's pointing into the screen. And again, we use these little arrows to represent a field that goes into the screen. And then we say, suppose that I take a particle, and let's say that it's a positively charged particle that we call Q, and we give it a velocity vector, and we make the velocity vector here, I'll try to make it straight to the right. That's its velocity. Then we found last time that there's this type of a force, and I'll repeat what the force was over here. We learned that there's this thing we call the magnetic force, that it acts on particles that have a charge, but the charged particles have to be moving, so they have to have some velocity. And then in order to find the direction of the force, we have to use this thing called the right-hand rule, but that is the definition of what the force is. It's QV cross B. So in this picture, can you guys tell me, if you use your right-hand rule and you point your fingers in the direction of V and you rotate from V to B, where B is pointing into the page here. Sorry, this is the magnetic field that's going into the page. What direction would the force on this particle be? Up, that's right. You remember from last time, or you did some studying. Good job. The force is this way. That doesn't show up as well. Let's use red. That's the force. I don't need to draw a huge vector. That's the direction of the force. And then when you have a velocity at this direction and a force at a right angle to it, so if this is a right angle right here, that means that the path that this particle is going to travel along, it's going to tend to rotate it so it travels kind of up to here, at which point its velocity is now going to be pointing straight up. And now the force, if you check, you'll find that the force is inwards as well. And you can get an idea that if this is what the particle does between these 2 points, it's going to continue to do that. The force is always to the left, so this particle is always going to turn to the left. And if you're always turning to the left, the motion that you move along is a circular path, like that. And we're going to define the radius of the circular path to be r. And then we're going to say that anything that moves in a circle, we can say that the net force that's acting on that particle in the radial direction should be equal to the mass of the particle times its radial acceleration. But when a particle is moving in uniform circular motion, its radial acceleration is given by v squared divided by the radius. The only force that's acting on this particle is the magnetic force, and the magnetic force is going to be equal to qv times b, because the angle between velocity and the magnetic field is 90 degrees. You'd put times sine 90 here, right? Because to get magnitude out of this, you would be doing qvb times the sine of phi. That's going to be equal to the magnitude of the force. Running off the screen here. I should erase this because now one's a vector and one's not. And if we rearrange this, okay, then we can solve for the radius. We can solve for whatever we want to, really. But if we solve for the radius, draw, click, click, we say the radius then is equal to mv divided by qb, I think, right? Does that look right to you guys? Yeah. Here we go. We could also find, if we want to, the angular frequency that the object moves along, right? Because there's this relationship that says that angular frequency omega is equal to velocity divided by radius. Does that look like something familiar to you guys? So if we rearrange this equation, you can prove pretty easily, you can prove for yourself if you want to, that if we take QB and we divide by the radius r, then we're going to get, I think, omega. No. It's QB over m. Should be equal to V over r. And that's equal to omega, the angular frequency. That would be the radians per second. This symbol means angular frequency or angular speed. All right. Does that make sense to you guys? So we're going to do this problem here, the helical motion of a particle, but I wanted to show you guys this picture before we do it so we can talk about what's going to happen. Ooh. Okay, there we go. I could probably make it a little bit smaller. So we just described that a particle can move in a circle if you place it into a uniform field, but the thing that I didn't include, I said specifically here that the velocity of the particle was in the plane of the page, so it's exactly at right angles to B, right? But what if the velocity of the particle has a component, let's say, that comes kind of out of the page? Like add a component here, maybe that points in the same direction as the magnetic field, okay? If the velocity vector has a component that points in the same direction as the magnetic field, this is what the particle is going to do. The magnetic field can't actually change the speed of the particle. Does that make sense? It can only alter the direction that it's moving. You guys understand? Because the vector for the force is always at right angles to the velocity vector, it can never speed the particle up, right? All that the magnetic force can do, it acts like the steering wheel in your car, right? The steering wheel in your car can't actually make the car speed up, right? You guys agree? Your steering wheel can't make your car speed change, but it can change the direction of your velocity vector, right? You can go from pointing one direction to turning left, right? Which means that your steering wheel is capable of changing your velocity. It's just not capable of changing your speed. Do you guys understand? Does that make sense to you guys? So the magnetic field does the same thing. It can only turn the particle left or right. It can't make the particle speed up, okay? The magnetic force actually, we often say, can't actually do work on the particle because the force is at right angles to the velocity, right? So if the force is at right angles to the velocity, that guarantees that the work done is zero. You guys understand that? Because work is equal to force times displacement, and if your displacement is always at right angles to the force, you get no work done, right? So some things you can say here is basically that the magnetic force can change direction, not speed. And in general, the magnetic force can't actually do work because it's always at right angles to the path the particle's traveling along. Can't do work, and it's you can compare this to like the normal force, for example. Right? The normal force can't do work because it's always at right angles to whatever surface you're on. Okay, so does this part make sense? That if you give the particle a little bit of a vector velocity parallel to the field, and that's what's being done right here, that it's actually going to keep going in a circle, but it's going to keep that velocity vector forwards, and so it's going to keep kind of going. It'll travel on a helical path like this. I've got a video of that here. I closed it. Oops. There we go. That's what I Googled. That's not the one I want, though. This was the only one. This is the one. I tried to find an actual video of this, but we actually can produce this type of motion in the lab. It's just too bad we can't go to the lab. Like I could show it to you in a lab, but I couldn't find any videos showing it here. So this is just an animation. So you've got a magnetic field that points straight up here, and you've got a positive particle, I believe, down here, and the particle is just given a velocity vector that points kind of slightly tilted upwards this way, and you can see the type of path that it goes along. Oh no, it's coming out towards us. My bad. That's just the kind of path that it would go along, going in a circle because of the magnetic field, and going upwards because it has an upward momentum to carry it that way. You can imagine, actually, that if you were in a reference frame that was moving along with the particle upwards, what would it look like? What if you were moving upwards at the same speed that the particle is moving upwards? What would its motion look like? Does the question make sense? That's right. Do you guys understand that? Like, if you were moving upwards relative to this particle, it would just look like it was moving in a circle. It would go in the same path circle, right? So really, this is like a relative motion kind of thing. Like, the only reason it looks like a helix is because we're at rest relative to the particle, right? And so it gives you this helical pattern. But if you were to move along to the right at the same speed that the particle is moving to the right, it would just look like a circle. So it's just the nature of, like, adding an additional component that doesn't experience a force. Of course, if you added a electric field to this picture, things could be different, and the path would be different. But we're just looking at what happens when you only have a magnetic field. All right, so we're going to do this we're going to do this problem about the helical motion in a magnetic field. This is pretty similar to one of the homework problems in this chapter, I believe, that you guys have. Let me move some of this stuff off the screen. This is for the next problem we'll do, and this one we probably aren't going to get to. Do you guys have any questions before I move on about this circular motion? Can you guys envision what's happening in your head? One other thing I want to mention is, like, if you think about what the charged particles do when they encounter magnetic fields, they basically just, you see what they're doing? They kind of like get trapped by the field. And that means that particles like this are going to like loop around magnetic field lines, right? This happens at the North Pole of the Earth. Charged particles coming in from space get trapped by the Earth's magnetic field, and they spiral down into the Earth's magnetic field, and they interact with gases in the atmosphere, and they produce this effect called the aurora borealis, what's called the northern lights. Just by particles getting trapped in the Earth's magnetic field. The Earth acts like a little bottle or vacuum that sucks up charged particles from space, and when they hit our planet, they make these beautiful colors called the aurora borealis. But yeah, particles get stuck in these magnetic fields. All right, so this is the problem we want to do. It says, in a situation like that shown in this picture here, the charged particle is a proton, and the uniform 0.5 Tesla magnetic field is directed along the x-axis. At time t equal to 0, you're going to see them one day. Yeah, I really want to go and see the aurora borealis too. I definitely have to get up there. You can only see them from, so it's either the northern hemisphere or the southern hemisphere. You need to be pretty far north. Like if you're in Scandinavia, I believe you can see them. If you're in Alaska and northern Canada, you can see them. Apparently they're really beautiful. I definitely want to see it. All right. So we've got some information here. I'll just write down over here that B is equal to the magnetic field, so that's 0.5 Tesla. And I believe it says that it's directed along the x-axis, so we can give a vector for this, right? We can say that the magnetic field is going to be 0.5 Teslas multiplied by I hat. We have at t equal to 0, the proton has a velocity with components of Vx equal to this and Vy and Vz equal to this, right? So let's just write it like this. The velocity V is going to be equal to 1.5 I hat, no j hat component, so plus 2 k hat, and then this is all multiplied by like times 10 to the 5th, right? So times 10 to the 5th meters per second. It says only the magnetic force acts on the proton, so there's no other forces acting here that we need to worry about. We want to, at t equal to 0, we want to find the force on the proton and its acceleration. So we've got a charge, right, Q, and a mass, and our goal is to find force, right? So this is where we'd want to use the equation that we've been using so far this semester, or this chapter, which is that magnetic force is equal to charge times velocity vector crossed with magnetic field, right? So what are these things? Well, we know the charge. Q is 1.6 times 10 to the negative 19 multiplied by V. So you put in here okay, there's our velocity vector. And we need to take the cross product of this with the magnetic fields. Okay. So this is where we have to remember some things about cross products. If you're little bit rusty on this. So I'm going to remind you that if I have a coordinate system, and this is x, this is y, and this is z, then I have unit vectors that point along those axes, right? This is what we call the I hat vector. It points in the x direction. And this is what we call the j hat vector, which points in the y direction. And this is what we call the k hat vector. And when we have these set up like this, you can answer questions like this. What is I crossed with I equal to? What's I hat cross I hat equal to? Zero. That's right. It's 0. It's 0 because the angle between I and I is 0. And to do a cross product, you take the magnitude of the first vector times the magnitude of the second vector, which is 1 times 1, times the sine of the angle between them, and the sine of 0 is 0. Okay, well, I cross I would be this one crossed with that one, right? So that's going to give us 0. What about the other term, which is k cross I? What's that equal to? The magnitude is 1, but the direction is going to be one of the other vectors, right? So if you point your fingers in the direction of the z, which is coming out of the screen, and then you rotate your fingers to x, which is to the right, what direction does your thumb point? It's j. It's positive j hat. That's right. So k cross I is j hat. So what we're going to get out of this whole equation then, 1.5 I hat is going to give nothing. So we're just going to multiply everything through. And I guess I'll pull the calculator up. So we're doing 1.6. Oh my god, how does this thing... I haven't had to do these on here yet. Times 10 to the... Yep, I knew it was going to do that. Oh my god. We're going to go... And we're going to get a better calculator than this, because this is awful. We're going to use this one. This one's really good. Assuming they haven't changed it recently. Oh man, this black background is scaring me. Maybe they did change this. Let's try this one. What's going on? It's just not loading it. It's disappointing. That calc is bad, Bernardo says. Yeah, it's really awful, isn't it? Oh, here it is. Good. Okay. I love this calculator. This one's really good. All right. I don't want to do that. I can close this, right? Yeah. All right. So we'll just make this the same size as my window. No, don't do that. Is that enough? I think that's enough. All right. So I'm just typed this in. So it's 1.6 times 10 to the negative 19. I think it trusts that. I think it does that, right? Yeah. So 1.6 times 10 to the negative 19 times 2. We don't have to do the 1.5. It's going to be 0 times 2, and then times, so it's basically 2 times 10 to the 5, so we'll just do like that, and then times 0.5. My god, that's so much easier. So the answer is 1.6 times 10 to the negative 14, and that's the force. And it's times j hat, because k cross I was j hat, right? So that's the direction of the force. Okay. All right. That would be the force, I believe, when it's on the bottom, right? Because the velocity vector was I hat was to the right, and this one didn't do anything, so it was the k hat vector. No, it's actually when it's on the bottom, right? It's like when it's down here, for example, because then the velocity vector points like that. At least that would be vz. And the force vector, then, we're saying, would point upwards like that. I don't know if that's visual enough that you guys can understand what's being said here, but does that seem right to you guys? Because this is positive and this is positive, so vz is going to point this way. So it's when it's on the bottom. All right, that's our force. How do we find the acceleration? That was the other thing. Force on the proton and its acceleration. How do I find the acceleration? Yeah, so the acceleration is going to be equal to the magnetic force divided by the mass. So we take that number over there. and we divide by the mass of the proton. This is in newtons. It's still j hat, because the force is going to be, the acceleration is going to be in that direction. We divide by 1.67 times 10 to the negative 27. Anytime you have a problem with a proton, it's not always going to tell you this, but you can look this up in the internet if you want to, and then we can come over here. So it's 1.6. Oh god, not that thing. Please no. So it's basically 1.6 e negative 14 divided by 1.67 e negative 27. 9.58 times 10 to the 12. Extremely high acceleration. An unreasonably high acceleration, maybe. What was it? 9.6 times 10 to the 12. This is an acceleration that's high enough that you have to start including what are called relativistic effects, where the laws of mechanics no longer apply, and you have new rules to stop particles from ever reaching the speed of light. Although this acceleration is directed towards the center, so it can't actually accelerate the particle now that I think about it. So it doesn't really matter how big this is, because this is an acceleration that causes the particle to turn, not to accelerate. All right. Do you guys have any questions? No? All right. Part B. Find the radius of the resulting helical path, the angular speed of the proton, and the pitch of the helix, the distance traveled along the helix axis per revolution. Okay, so in order to do this, we want to find first the radius of the helical path. So our equation from before was that the radius of the path would be given by this expression right here. This expression here. That's how we're going to find the radius. But one thing that I kind of left out about this is that the only component that's going to feel this kind of a force, and therefore the only component that's actually going to contribute, is going to be the component that's perpendicular to the magnetic field. So in our case, that's going to be just the z component of the, there we go. The z component of the particle's velocity is the only component that's actually going to affect the radius now. Because, I mean, think about what we did up here on this picture, right? It was only the component of the velocity that was actually perpendicular to the field. But we also found that the force right here was determined only by that same velocity component. The z velocity component is the only thing that created this force. And so as a result, it's the only thing that's going to have anything to do with this radius here. Because after all, this radius came from using Newton's second law, right? It was the radial component of the acceleration, which is coming from the velocity component that is perpendicular to the field, the z component down here. Right? This component is perpendicular to the field. All right. So, given that that's the case, we can solve this now. We know. Does that all make sense to you guys? Does anyone have any questions? No? Okay. Rapidly running out of time here. So that multiplied by Vz, and Vz was this 2 times 10 to the 5. And we divide that by charge. Magnetic field. And we just calculate that. We get 0.004175, or something like 4 millimeters, 4.175 millimeters. Oops. Very tiny little radius. Any questions about that? We also want to find the angular speed of the proton. That's basically this velocity divided by, well, we can also just get it from here, right? QB over m. Oh, didn't. Here. So that one is. Well, it's basically the inverse of what we just got. Well, we'll just go calculate it again. My god, that number seems huge. But it has to be huge because it's negative 27 in the denominator. I want to check the units for this in a second, make sure we got the units right. So we end up getting, what is that number? Like 4.79 or about 4.8 times. Is it 10 to the 7? And then the units of this should be radians per second. We're going to check the units though. Is that 7? 1, 2, 3. 1, 2, 3. Yeah, it's 10 to the 7. Does that all look right to you guys? Let's check the units. All right, so we've got units of coulombs. We've got units of Teslas. Just to remind you how you figure out the units of Teslas in case you don't know, you use this equation, FB is equal to QVB, and you just solve it for B. So B is equal to FB divided by, so B is equal, yeah, divided by QV, which means your units are basically newtons divided by coulombs times meters per second, or newtons per amp meter, however you want to do it. So I'll just put in here that the units for B, that's what we're doing now, are newtons divided by coulomb times meters per second. All of this in the denominator. Oh, it's even worse if I write it like that. Let me just say it's newtons divided by coulombs and then meter per second right here. And all of that, put in parentheses, and all of that's divided by the units for mass, which is kilograms. Units for this then are going to be, the coulombs will cancel, the newton is a kilogram, a meter divided by seconds squared, and that's divided by a meter per second. It's also divided by a kilogram, so you can see pretty quickly that all the things you need to cancel out, and you're left with just 1 second that's in the denominator, so you get the units of 1 over seconds, but it's actually going to go to radians per second, because that's what happens when we describe things by doing V over R. So that's the unit. So it does work out. That's good. So this is the angular frequency. That's the rate at which it's looping around, right? It literally is going to go through, I mean, radians are hard to think about. You could divide this by 2 pi, which is about 6. So let's just say about 1 times 10 to the 7 is the frequency. About 10 megahertz is the frequency at which this thing is spinning around 10 million times every second. It goes through one of these little oscillations. If that makes sense. Kind of crazy to think about. It's really fast, isn't it? Okay. Do you guys have any questions? Someone's typing a question. That's great. I'll wait. And then he stopped. Okay, so the last part is to find the pitch of the helix. Okay, and that's the distance traveled along the helix axis per revolution. How would I calculate that? What should I do to figure that out? It's basically like the distance between... It's basically like the distance between one of these little loops. How could I figure that out? What do you guys think? How could I figure that out? Any ideas? Do you want me to just tell you? Yeah, what is omega? How? Oh, sure, let's do that. How would we do that? How would we find the time it takes to go through one circle if we know the rate at which it's going around? We want to calculate this thing, right? Period. You guys remember the relationship between this and this? You're on the right track. It's the time for one cycle, right? And one cycle would be how many radians? So everyone knows that. Everyone knows that it's 2 pi radians per cycle, right? And you just have to divide by omega then, because this is the number of radians per second, and that'll give you the seconds per cycle, right? Because omega has units. I'll write it out. It's 4.8, times 10 to the 7 radians per second. You can see how it works out, right? This gives you cycles, or seconds per cycle, right? This ends up giving you whatever the answer is. Let's see. Oh, 2 pi times 10 to the 7. My bad. Where's my calculator? So we end up getting 1.31 times 10 to the negative 7. This is part C, by the way. This was part B. Oh, there is no part C. This is still part B. That's in seconds, right? And now, what do we use that for? Someone said this is what we wanted to do, but what do we use that for? Because our goal was to find... Go ahead.
We multiply it through the horizontal plane of velocity.
Yep. Just take the x component of the velocity, which I think was 1.5, right? Yep, this one. 1.5 times 10 to the negative 10 to the 5. So if we take... Because that's how fast it's moving in the x direction, right? And that's what we want to find, is how far in the x direction did it move. So we take 1.5 times 10 to the 5 meters per second, very fast velocity, and we multiply that times the time for one oscillation. And that gives us our answer. Probably do this in my head. I'm not going to. So it's... This calculator is way better, right? Have you guys ever used this before? Or something like it? So we end up getting delta x is equal to 0.01965. So that's like... If you compare the size of the distance that it moves to the radius of the path, it means that it moves quite far relative to its radius. So it would be sweeping out things like its spirals would be like kind of like long and loopy, like a really tight loop. My God, that's an awful drawing, but hopefully you guys get the idea. Okay, do you guys have any questions before we move on to other things? All right, we're going to talk about some specific applications of the magnetic force, and we're not going to go into detail about like how a maglev train works, although we will talk about that later. And we're not going to talk about magnetic railguns, but we will later. But we're just going to talk about some very simple applications of things you can do with this magnetic force in combination with the electric force. There are obviously tons of applications of what magnets can do, and we'll be discussing motors and generators and hoverboards and stuff like that later. But for now, we're just talking about very simple applications. And the first one we're going to talk about is called the velocity selector. So a velocity selector is very basic. All you need is to have basically this. Let me step back so I can draw better here. All right, so there we go. So suppose that I have 2 plates. So I've got one plate here, and I've got one plate here. And I charge the upper plate as positive, and we charge the lower plate as negative. we know that there's going to be an electric field in the region between the plates that's going to point straight down. You're going to have electric field lines that are going to go like this. And now suppose that we put a particle and we give it a velocity. Okay, so we have some charge right here that we call Q, and let's say that it's positive, and we give it a velocity, so it points into this little system right here. And let's assume that the velocity is fast enough that we don't need to worry about gravity. We only really need to worry about the effect of the electric field. What kind of path would this particle take the moment that it enters the field? Is it going to come in and go straight down? Is it going to come in and kind of go off like this? People can't see that. Is it going to go into the field and go straight down? Is it going to go into the field and kind of curve downwards? What's it going to do? What kind of path would this particle take? Yeah, it's going to be kind of like a projectile, right? It would tend to kind of curve off in a path, something like this. Kind of come down like that, right? It'd be parabolic, and yeah. But suppose that we, at the other end of our system, put a block like this, a little slit, okay? And let's say that these charged particles, that if they hit this slit, they get absorbed by it, but if they make it through, they pass right on through, okay? And suppose that we want to make it so that this particle can actually make it through. Well, we would need another force to counterbalance that electric force, right? And we could do it with the magnetic force, because we know the magnetic force is capable of also putting forces on charged particles, as long as they're moving. So suppose in the same regime, we put a magnetic field, and we'll use blue for the magnetic fields, dark blue. Let's say that the entire regime here is embedded into a magnetic field that looks like this, that points into the board, or into the screen that you're looking at, right? So that's our magnetic field. And we're saying that it points into the screen. And by the way, I didn't mention how you would do this, but I will say that if you take a magnet like this, that's like a north end of a magnet on this side, and I take over here a south end of a magnet on this side, right here, so this is how we orient our magnets, we can exactly produce the type of thing that I'm describing here, because the magnetic field in this case is going to point from here to here, from south to north. This is how you would produce a magnetic field like this. I can't show you this, but you'd put one magnet in front of the screen and one magnet behind the screen, right? And you can easily produce this type of magnetic field. You'll notice that this is very similar to the way that the electric field works, right? Electric field, positive, negative, straight field. Magnetic field, north, south, you get a straight field, right? That's just how it works. All right, so if I do this now, and we think about what would happen as the particle, let's say, is at this location here. Okay, so it's got some velocity vector that points this way. And if we think about what the direction of the forces on the particle are, it's going to have a electric force that points down this way, right? What direction is the magnetic force going to be? It's going to go up. If you use your right-hand rule, point your fingers in the direction of velocity, then you get that the magnetic force points up like this. And now, if these two happen to be exactly equal to each other, what path would the particle travel along? Straight line, exactly. If you have a particle that has the net force acting on the particle is equal to 0, it'll travel perfectly in a straight line. And that's very easy to do. We just need to make it so that the electric force on a particle is exactly the same as the magnetic force acting on the particle. The electric force acting on the particle, that's easy. That's just the charge multiplied by the electric field, right? The magnetic force, also very simple. It's just charge times velocity multiplied by the magnetic field. And now if we cancel out what we can cancel, then we find that the velocity of particles that will exactly make it through our system, right, are going to have a velocity that's equal to this. These particles will travel and make it through in a straight line. They'll make it through this little slit that we created here, right? And any particle that doesn't have exactly this velocity is either going to hit up here or it's going to hit down here. Which side would they hit? Let's call this top. Let's call this bottom. You guys tell me. If the particle is moving too slow, is it going to hit on the bottom or is it going to hit on the top? You guys understand the question? And then what's the reason why? I see people saying bottom in the chat. Why do you guys think bottom? What's the reason why? Man, it's not going to slow down. It's going to slow down so it'll go downward. I don't like that answer. The force would be weaker. That's right. Which force would be weaker? The magnetic force would be weaker, right? if the velocity is too slow, then the magnetic force isn't going to be very strong because it's proportional to the velocity, right? Exactly. So if the particle is too slow, it hits the top, or the bottom, sorry. And if the particle is too fast, then it's going to curve up, right? So a particle that's too slow, it's going to come in and it's going to go and it's going to hit here. A particle that's too fast, is the magnetic force is now going to be too big and it's going to hit on the top, right? Does that make sense to you guys? And the particles that have this is like the Goldilocks particles that have the velocity exactly equal to the electric field divided by the magnetic field, these ones pass straight on through. And that's why you call it a velocity selector. It allows you to control the velocity of the particles. And that means that you can have a species, a sample of particles that all have exactly the same velocity. Suppose that you have a source, okay? Suppose that you have like some kind of a source over here that's producing particles and it's spraying particles off in all kinds of directions. You want to focus that beam down into just like a nice fine beam of charged particles that all have a certain velocity. This is how you would do it. This is exactly how you do it at the places that I worked. We worked on systems where you had systems like this inside of them specifically to pick out exactly the particles that you want. The only drawback to the system is the particles have to be charged. So this will not work on neutral beams of particles, which unfortunately is some of the most interesting particles, like neutrino beams, which are made of neutral particles. We can't control in this fashion. And so we have to, just deal with what we have. We just can't control them yet. We would need some other type of force to control them. We know other forces that could control them, like the weak force. We just don't know how to control it well enough yet, if you know what I mean. Anyway, so that's a velocity selector. That's how it works. Does that all make sense to you guys? I'll probably talk about the other application too. We won't have time to do the problem. We'll do it next time. This is kind of impressive in its own way, right? It just happens to be the case that when you take the ratio of the electric field to the magnetic field, you just happen to get velocity. Isn't that interesting? I think this is interesting. These two things, electric fields and magnetic fields, and you think they have nothing to do with velocity, but it turns out the ratio of an electric field to a magnetic field has the units of velocity. That's surprising, I would say, to say the least. That kind of surprising to you guys? Anyway, what we're going to learn eventually, and you need to take 1D to learn this, but the magnetic field is nothing but an electric field viewed from a different reference frame. That's all it is. You know how like someone sitting still on the road, like someone sitting on the side of the road, if you drive past them, it looks like they're moving away from you. So they're sitting still relative to the ground, but it looks like they're moving away from you. Well, an electric field, if you move relative to it, it starts to look like a magnetic field. So anyway, it's just how it works. And this is what Einstein realized. He realized that the magnetic field was nothing but an electric field in motion, and he used that to produce this theory called special relativity. And you'll learn all about that stuff in 1D. I don't know if you'll go into the details of like how the magnetic field transforms into an electric field and stuff like that, but you might. Who knows? Those of you that are taking 1D this semester, I can do like one extra lecture at the end and talk about it if you guys want to, because it's really fascinating. Okay, one more application. And this may be something you've used before. I don't know. Have you guys ever used a spectrometer before? In your chemistry classes, maybe? You guys ever used one of those? In labs you have? Okay. So this is pretty much how it works. So you start off with, here, let me see if I can't just copy what we had from before so I don't have to redraw it. Because you start off with basically the exact same thing. So let's take this, copy it, paste it. Can I rotate? That's what I really want. I want to rotate this. Okay, I don't have to rotate it, do I? No, I don't have to. So we start off with a velocity selector. We've got our particles, and they all come out with a certain speed. And then the next thing we need to do is we need a secondary magnetic field once they actually exit. So we'll use light blue for this. So let's say in this regime over here that the magnetic field actually came out of the board. So we've got a magnetic field over here that comes out of the screen. So here's our magnetic field. We'll call it B prime, and we're going to say that it points outwards. Probably drawing way more dots than I need to do here, but whatever, you get the idea. There's this regime where you've got this magnetic field, and it's coming out of the board. So dot, 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 dot. You get the idea. Magnetic field all in this region here. And then here what we have is some type of a screen, like a fluorescent screen. Fluorescent screen. There we go. That's what this whole thing here is, fluorescent screen. And now what happens is that suppose a particle comes out of our machine here, and it comes out with a velocity in this direction, okay? We know the velocity of the particle was equal to the electric field divided by the magnetic field, E over B. That's what we proved in the last part. Is it E over B or it's E over B right there, yeah. That's the velocity it comes out with. But now, once it gets into this regime, the path that it's going to take, what's the direction of the magnetic force on this particle? Is it up or down? It's definitely down, right? Force was up here because the field was in. Now the force is going to be down. So the path that my particle is going to travel along, I want to use black for this. The path of the particles, I want to use black for this. Can I pick black? If I just change this one to black, then if you won't let me pick black. Okay. So the path is going to be like a semicircle, right? It's going to come up and it's going to go in a semicircular path. That's awful. It's like an oval. It's going to go in a circular path, basically, right? It's going to come out this way. It's going to come down this way. This is a semicircle. It doesn't look like one, but it's definitely a semicircle. All right. And that semicircle is going to have some radius, right? R. And we also know what the radius is. The radius is equal to the mass of the particle times its velocity divided by q times b. In this case, that's going to be b prime, this thing out here, right? So what's going to happen now is if you have a particle that has, so let's say this is one particle and that's what it does, and the radius is given by this, right? And we call that one like radius r1, say mass m1, and charge q1. The velocity is still the same from before. All the particles are going to have the same velocity, right? Suppose now that I bring a particle in here, and let's say that it has exactly the same charge as the first particle, but let's say that it has a smaller mass. What type of circle would it move on if the mass was smaller but the charge was the same? Would it be a bigger circle or a smaller circle? Some people say small, some people say big. What does the math tell you? If V, B prime, and Q1 are all the same, and M2 is smaller than M1, what happens to R2? Is R2 smaller or bigger than M1? Or R1? You should be able to... No, not R1. There we go. This. You could also just think about it that like it's a smaller particle, so it has less inertia, so it can't go as far, right? So this way, if this is R1, then R2, use purple or something. R2 would be a circle that would be something like this, maybe. All right, so I'm sure the way I asked the question was confusing, so I wrote it down. Hope it's clear it's written down, sorry. So, wow, I didn't even draw the radius from the right spot. The radius of circles come from there. There we go. Okay, so I hope that made sense. A mass spectrometer has the effect of splitting up your species into a bunch of different points that they hit, right? And the way that the spectrometer, I think, actually lists things out is it counts the number of particles that actually hit at this location, and then it counts the number of particles that hit at this location, right? And you can use that to figure out, let's say you have a chemical and you're trying to figure out what the chemical is composed of. This allows you to figure out what it's composed of. And I think that's kind of probably where you guys use it in your chemistry classes. Am I right about that? I don't know. You guys tell me. Yeah, exactly. Okay, good. So that's a mass spectrometer, and we'll do a problem with it. We can just do the problem right now, actually. Let's just do the problem. We have time. It doesn't take very long to do. So, all right, this is the problem. It's pretty neat though, right? It's just the fact that like, it just, the way that this works is that it splits up particles. Like the less massive particles show up closer to the detector, and the more massive particles, they get farther away. In addition, if you have a larger charge, then also the radius gets tighter, right? So really what this thing allows you to see is mass divided by charge. It's that ratio that you're seeing. It's M over Q that you're seeing. That's one of the things you would have calculated if we did this lab in our class where we used... anyway, so it's the mass over the charge that you're really seeing right there. All right, so this is a problem we can do regarding this idea. This is, I don't know if I assigned this problem in your homework or not. Even if I did, it doesn't matter to me. It's a good problem to talk about how you use these things. So you have a singly ionized, i.e. one electron removed, krypton. Is K krypton? Krypton 40 atom passes through a velocity selector consisting of a uniform perpendicular electric and magnetic fields. The velocity, potassium, thank you. Okay, sorry about that. Krypton's Kr, right? Potassium, yes, that is what K is, thank you. Okay, the selector is adjusted to allow ions having a speed of 4.5, so that's our velocity. 4.5 kilometers per second. That's coming out of the velocity selectors. We also know this is equal to E over B inside the selector. It says, have a speed of 4.5 kilometers per second to pass through an undeflected when the magnetic field is 0.025 Tesla. So we also know that B is equal to 0.025 Tesla. The ions next enter a second uniform magnetic field B prime, oriented to, we don't know what B prime is, I assume, oriented at right angles to their velocity. Potassium contains 19 protons and 21 neutrons. Wait a minute. It's set up here that it was one electron removed. So it's just going to be positive 1 for the charge, right? I mean, this information about how it has 19 protons and 21 neutrons isn't really important, is it? Wouldn't so one electron removes means this is going to be a positive ion, right? So yeah, the charge should just be plus, whoops. Yeah, the charge should just be positive 1 times the electron charge, or 1.6 times. I think this is the charge. I think they're just trying to confuse you. Why do they do this? Whatever. Okay, and has a mass of 6.64 times 10 to the negative 26. So there's our mass. You think it means per atom is 17 electrons? No, there'd be 18 electrons, right? There'd be 18 electrons. Anyway, 6.64 times 10 to the negative 26 kilograms. Okay. 2 things we want to calculate. What is the magnitude of the electric field in the velocity selector? Well, that's really easy to do, right? Because the electric field is just going to be equal to B times V, velocity times magnetic field. We have those numbers, so 4,500 meters per second multiplied by the magnetic field, which is 0.025 Tesla. All right. Probably could do that in my head, but I'm not going to. Basically, just dividing by 1 over 40. Whatever. We'll just put it in the calculator. Oops. So, oops. Okay, that's the electric field. And then what must be the magnitude of B prime so that the ions will be bent into a semicircle of radius 12.5 centimeters? So we know the radius is going to be equal to 0.0125 meters. No. 0.125. And we just want to calculate what B prime is, right? So we can go back and grab our equation from before, which was this one, I guess. So we want to solve for B prime. So I'll just rewrite the equation. The equation is R equal to mv over q B prime. So B prime is going to be equal to mv divided by q times R plugging in the numbers. I think I don't want to write all these again, so I will just pull this up and we'll type them in. Let's see, so mass is 6.64 times 10 to the negative 26. And then velocity was 4,500, I think. Divide by q, backspace. So divide by 1.6 times 10 to the negative 19. And then divide by the radius, which was 0.125. And that is 0.0149 Teslas. That would be the magnitude of the magnetic fields in the outer region, which would be like this region out here. Okay, some of these problems are really easy. I think most of it is just understanding the words, but the actual equations themselves are pretty simple. Next chapter will be a little tougher, just so you guys know. In the next chapter, we're going to have to talk about developing a magnetic field from electric current, and that can be really quite complicated. So things are going to get kind of tough for another chapter or two, but then they'll get easy again. So that's magnetism. We didn't get to talk about the effect of magnetism on current carrying wires, so we'll talk about that next time. And then from there, we'll go into talking about sources of magnetic fields and stuff like that. But that's all for today. I will stick around if you guys have any questions at all. I'd be happy to answer questions about homework or just general things about the class. But that's it for today. Do you guys have any questions about the lecture before I stop the stream? Or stop the recording?